Welcome back, everyone. In this video, we are going to talk about calculating the nominal moment capacity of a reinforced concrete beam. Let's begin again with a discussion of our moment curvature relation for this beam. So there are three regions: the uncracked region, which ends at M crack, the cracked region, which ends at yielding, and now specifically we are looking at the final branch where we're taking it all the way to failure. Now, this moment is known as the nominal moment capacity, M sub n. It's not that much bigger than the yield moment, but it will be slightly larger. And it's defined by an ultimate strain in my concrete equal to 0.003. Now, the behavior of this, we've already formed cracking at midspan, but we're going to be crushing the concrete here, and that's going to signify the ultimate failure right here. And that crushing looks like a total destruction of our concrete, as we see right here, with very large flexural cracks at that location. In order to calculate the moment capacity, we first need to look at our stresses and strains. So let's start with the strain diagram through our cross-section. So if I here have strain, we know the strain at the top surface is going to be equal to 0.003 because that's the crushing strain of my concrete. And then my strain will vary linearly through my cross-section, and so I have some strain here in my steel, and I'm going to call that epsilon t. That's my ultimate tensile strain. And that value, of course, has to be greater than yielding for a well-designed section. It is possible for a compression-controlled section for this to be less than yielding, but that is for another day. So right now, our strain diagram looks like that line through the section, and our stress diagram is going to be a little bit more complicated. So if we have a stress in our steel, because that's yielding, it's Fy. We're going to assume that the concrete in tension holds no stress. And that's similar to the cracked assumption. But in compression, if I draw my neutral axis over here, we'll see that it's not a linear relationship. It's this sort of curved shape where my peak F prime C, that's my ultimate concrete compressive capacity, is not actually at the top of the section. It's somewhere in the middle. Now, we can, if we have a stress strain diagram, consider this curved shape, but oftentimes we don't know that shape directly. So what instead we're going to do is approximate this using what's called the Whitney Stress Block approximation. So to approximate this curve, we're going to draw a rectangle here. And the stress in this rectangle is 0.85 F prime C. So think of that as sort of an average stress over this compression region. And the depth of that block is equal to A, which is beta 1 times C, and C is the depth to our neutral axis. The beta 1 factor is going to depend on the concrete strength, and we'll cover that in just a little bit. For right now, all we need to know is the value of A. So now I have a compressive force associated with this rectangular stress block. I have a tension force associated with my steel. That's yielding. So first we need to consider equilibrium. And for equilibrium, that states that our sum of forces is equal to 0, and therefore my tension force is equal to my compression force. Now the tension force, we have a stress Fy, and it's going to be multiplied by my area of steel As. So that tension force is ASFY, and that has to be equal to my compression force, which is a stress of 0.85 F prime C, and it's going to be applied over an area, this rectangular area in my section of B, which is the section width, multiplied by A, which is the depth of that block. So therefore, my compressive force is 0.85 F prime C times A times B. And because I don't know the quantity A, we can use this equation to solve for A, and therefore A is equal to ASFY divided by 0.85 times my concrete strength times B, the width of the section. All right, now we can use that quantity to find the moment capacity. So if I'm considering my moment, if I take the sum of moments about this section, that is going to give me my nominal moment capacity M sub n. Now, let's assume that I'm taking my moment about the centroid of this block here, and therefore I have one force that's causing a moment associated with my tension in my steel, and it will be a distance d minus a over 2 away from the centroid of that block. So therefore, M sub n is just equal to my tension force divided by the moment arm d minus a over 2. And therefore, my nominal moment capacity is AS Fy multiplied by D minus A over 2, where A is the depth of my compression block, and that is solved for with my first equation right here. So again, to reiterate, that is my nominal moment capacity, and it's equal to my tension force AS Fy multiplied by a moment arm D minus A over 2. Now, we made a core assumption on the way here, and that assumption was that my strain in my steel was greater than yield, effectively that my stress here was Fy. We probably want to check if that's true, and so in order to do that, we need to find our depth to neutral axis C. So let's go ahead and look at that. So now if we're looking at C right here, we know by definition that our compression block A is equal to beta 1 times C. So let's just flip that around and we'll say that C is equal to A divided by beta 1, where beta 1 is going to depend on our concrete strength. So ACI 318.19 classifies 3 different categories of strength. We have low strength, middle strength, and high strength. And that classifies our beta 1 value. For low strength is 0.85. For high strength, it's 0.65. And in between, it varies linearly according to this expression. So that gives us a depth to our neutral axis. The next thing that we can do with that information is find a curvature. So if we want to look at a curvature, that's simply the strain divided by some distance. So my curvature in this case, the strain is 0.003 on the top of this section, and that's being developed over a distance of C. So that is the distance from 0 strain up to 0.003, and that's actually it. That's all we need to calculate our curvature. And lastly, if I want to find my strain in my steel, we can use similar triangles to find this. So because I know I have a triangle here and also a triangle here, those two are similar triangles, and so I can just use similar ratios. And if we evaluate that ratio, we'll find that epsilon T in the steel is the concrete strain, 0.003, multiplied by D over C minus 1, where the depth D is the distance from the top of my section down to the layer of steel. So we're going to want to check that value. Specifically, we want to make sure that it's yielding, but we also want to make sure that it is high enough above yielding so that I have a ductile section behavior. So once again, in ACI 318.19, we have this figure right here that describes our strength reduction factor for 3 different failure mechanisms of our beam. We want to shoot for the tension-controlled mechanism. That gives us the best strength reduction factor of 0.9, and we want to avoid the case where we have a compression-controlled failure down here, where unless you have spiral reinforcement, that gives you a 0.65 strength reduction factor. That's a pretty hefty penalty there. If you're in between there, so you have some yielding, but not a lot, that puts you in the transition region where once again, we have this linear equation where we can do interpolation to find that strength reduction factor. But in general, when you're doing design, you always want to aim for this region. And that requires us to have a strain in our steel that is 0.003 greater than yield. Now let's take this knowledge and apply it in an example problem. For this problem, we're going to assume normal weight concrete of 5,000 PSI for the strength. I have grade 60 steel, and I want to find my nominal moment capacity, my steel strain, and my ultimate curvature. First thing we need to do is find the compression block depth. So my compression block depth A, we just had the equation for that, is ASFY divided by 0.85 F prime C and B. So my area of steel in this case, I have 3 number 9 bars, and therefore my area of steel is exactly 3 square inches. So plugging in these values, I have 3 inches squared for my area of steel. Fy is my yield strength for the steel, which is 60 KSI. And I'll divide that by 0.85. F prime C is 5 KSI for the concrete. And then my width of the section is 16 inches. And therefore, calculating all those numbers, I find my depth of my compression block is 2.65 inches. Now, given that compression block depth, I can go ahead and I can find my moment capacity M sub n. And this is equal to ASFY multiplied by D minus A over 2. So once again, I have all these quantities. So it's a relatively simple process. AS is 3 square inches. FY is 60 KSI. My depth D is the distance from the top of the section down to the centroid of the steel, which is 23.5 inches in this case. So 23.5 inches minus A over 2, which is 2.65 inches divided by 2. So running all those numbers, this is 3,992 kip inches. And I want to divide that by 12 so I can get this into kip feet. So 1 foot per 12 inches gives me a kip feet answer of 333 kip feet. Cool. So that is my nominal moment capacity for this beam. So the next thing I want to do is I want to check to make sure that my steel is yielding. I will also calculate the curvature just for informational purposes, and I'll also find the phi factor to make sure that I'm in the tension-controlled region to get my ultimate design capacity, which is phi times mn, or phi times my moment capacity. So first, if we want to check our curvature, I need to find that depth to neutral axis. So step 3 here is going to be my depth to neutral axis is equal to my depth of my compression block divided by beta 1. Now, my concrete strength in this case is 5,000 PSI, and that puts us in this middle range right here. So I'm going to have to apply that particular expression to get my beta 1 value. So here I have a beta 1, it's equal to 0.85 minus 0.05 multiplied by 5,000, my strength, minus 4,000 divided by 1,000. And we'll see that's equal to 0.8. Given beta 1, I can now find my depth to neutral axis, which is just equal to A, which is 2.65 inches, divided by beta 1, which is 0.8, and therefore this is 3.31 inches down from the top of my section. Now, given that depth to neutral axis, I can find my curvature, and this is a very simple process because I know the ultimate strain in my concrete is 0.003. So I just need to divide that by the depth to neutral axis to find my curvature. Therefore, we'll plug those numbers in. My curvature at ultimate is 0.003 divided by 3.31 inches, which gives us 907 times 10 to the negative 6th, 1 per inch. And again, that's strain per inch, but strain being a unitless quantity, this just has units of 1 over inch. Now, if we compare that curvature to our curvature that we saw at yielding, it's about 7 times bigger. So that is a significant amount of ductility in our section because we have yielded that steel quite a while back. But how far back was that? Well, let's calculate our strain in our steel. Now, for the steel strain, we need to consider epsilon t is equal to 0.003 multiplied by d over c minus 1, where this expression is coming from the idea of similar triangles through the depth of my cross-section. So once again, d and c are known quantities, so I can calculate my steel strain, and this is 0.003. D is 23.5 inches from the top, and my depth of neutral axis is 3.31 inches, which I just found. All that minus 1 gives me a strain of 0.018. Now I want to compare that strain to my yielding strain, and that is the yield stress divided by the modulus. And so I have 60 KSI steel. The modulus of steel is always 29,000 KSI. So if we divide those two numbers, we find that this is 0.002. So first of all, we see that yes, we yielded this thing long ago, and that the difference epsilon t minus epsilon y is about 0.016. That puts me well into the tension-controlled region because all I need is a buffer of 0.003, and I have about 5 times that. So therefore, my phi factor that I'll be using for this design gets to be 0.9. So last thing, let's calculate our design capacity, which is phi mn, mn being our nominal moment capacity, which we just found, phi being our strength reduction factor. Well, that's just 0.9 multiplied by our capacity, which was 333 kip feet. And therefore, my design capacity is 299 kip feet. And that is how we calculate the capacity of a reinforced concrete beam in flexure. So as always, I hope you learned something. Please subscribe, and I'll see you next time.